Opdenacker from Bootlin. Today I'm going to talk about U-Boot's Falcon Mode, how to use it and how to port it to your board. First, a few words about myself. I'm the founder of Bootlin, a company that specializes in free and open source software for embedded Linux systems. We do development, consulting and training. I'm also a contributor to free software. I'm the current maintainer of the Elixir cross-referencer that makes it easy to study the sources of big C projects such as the Linux kernel, so you can check it out on elixir.bootlin.com. I'm also the co-author of Bootlin's freely available embedded Linux and kernel training materials that you can find on http://bootlin.com/docs, and I was the former maintainer of GNU Typist. The goal here is to boot faster. So U-Boot Falcon Mode is about reducing the time spent in the bootloader, and the name was chosen because falcons are the fastest animals on Earth. In this presentation, I'm going to show how to use the Falcon mode on the SAM-A5D3 Explain board from Microchip. So the first thing you need to understand is how your SoC boots. So here is a diagram from the datasheet for the CPU. So here it explains that the various strategies for booting. So the first thing the CPU will try to do is find some first stage bootloader, some bootstrap code from SPI flash, copy it to SRAM, the SRAM of the static RAM of the CPU, try to run it. If it doesn't work, it will try the SD card, otherwise NAND flash, otherwise another SPI flash, and then an EEPROM. So that's the global strategy. So now I can start to explain the normal Linux boot on the SAM-A5D3. So it all starts with the ROM boot, the ROM code that executes from the CPU. It's supposed to load a first stage bootloader from MMC, NAND flash, SPI flash into the SRAM of the chip, which has limited capacity, unfortunately. But the job of this first stage bootloader is to initialize DRAM, which has, of course, much more space, so that you can load the entire U-Boot from storage and run it from DRAM this time. And then U-Boot will be in charge of loading the Linux kernel from wherever it's found, on storage or on a network, and run it from DRAM as well. So the idea here is, since the U-Boot SPL is actually loading the U-Boot from to DRAM, instead of doing that, the idea is behind Falcon mode is to directly load the Linux kernel instead, also from storage to DRAM. So that's the same thing. We just keep U-Boot and hope to save some time. So the main advantage of Falcon boot is that you're saving time by skipping the full U-Boot. There's a drawback though. You lose the flexibility that's brought by U-Boot. So you have to follow a special procedure to update the kernel binary, the DTB, the kernel command line parameters. The main advantage though is you don't need the interactivity offered by the full U-Boot on a production device. And the Falcon boot mechanism works in the same way on all the SoCs on which the U-Boot SPL is supported, from U-Boot providing the bootstrap code as well. And this makes it easier to apply this technique on all your projects. So the first thing to understand to replace U-Boot is to understand how it prepares for the kernel to boot. So the first way, the old way, is the ATAGS way. So in this case, U-Boot prepares the Linux kernel command line, the bootargs environment variable, the machine ID and other information for Linux in a tagged list, and it passes the address of the tagged list to the Linux kernel through a register. The second way is the flattened device tree way, FDT, the standard way. So in this case, U-Boot checks the device tree loaded in RAM or directly provides its own from its own source code. Then it checks the specifics of the hardware, like the amount and location of the RAM, the MAC address, the present devices, and possibly loads corresponding device tree overlays and fixes up the device tree accordingly. U-Boot also stores the Linux kernel command line, again the bootargs variable, in the chosen section of the device tree. Another way is the fit image way, the new way actually. So in this case, the U-Boot bootloader will load the kernels, possibly multiple ones, device trees, initramfs images, signatures from a single file, that is called a fit image. That's actually used in particular for a secure booting, for booting recovery images, etc. So That's interesting because U-Boot just has one binary to handle, containing everything. In that case, U-Boot will also implement device tree fixups, of course. So here we want to do all this, the boot preparation, not in U-Boot, but in the U-Boot SPL. So there's a command that's provided by U-Boot, actually, that can be used to prepare this work ahead of time. So in this presentation, we actually just cover standard device tree booting, the FDT booting. U-Boot indeed has support for loading a fit image in the SPL, but that's still a bit experimental in my impression. And another constraint is that this code must fit within your maximum allowable size for the SPL. So if you can read about it at this URL. So here's how to use the Falcon mode. You'll first have to recompile U-Boot for support for a Falcon mode, that's SPL OS boot, and also for support for the SPL export command and the way you want to boot on MMC or NAND flash. Also make sure you set SPL size limit that corresponds to the SRAM size for your CPU. So on SAMify D3, it's 64 kilobytes. Otherwise, U-Boot won't complain when the SPL is bigger and the SPL won't work. Then you build the kernel legacy UImage file from the ZImage file. We'll explain how to do that. Set the kernel command line, that's bootrx. And load the UImage in RAMFS, if you have one, and device tree images to RAM as usual. Then the next thing is to have U-Boot execute the preprocessing before booting Linux, but just stop right before the execution of the Linux kernel. So the command is like bootem, so it's xpl export ftd of the kernel address, the initramfs address, and the DTB address. So this creates the preprocessed data that we call args that you can save from RAM to storage in flattened device tree format so that the SPL can load it and pass it directly to the Linux kernel. You have some environment variables in U-Boot that will help. There's fdt args address, the location of args in RAM, and fdt args length, the size of args in RAM. Another thing, if that's supported by your board, we'll explain that later. You could also set the boot OS environment variable to enable it, to enable direct OS booting. So here's example output from the SPL export FDT command. It looks like booting the kernel, but just it stops before doing it. Don't worry about the sub command not supported. I've had it for a long time. It doesn't hurt. It's like that. As promised, here is how to create the UImage file. So you can either create it from the make command line from the kernel make file. So you pass a load address, that's usually the start of RAM plus 0x, 8 and 3 zeros. Or you generate using U-Boot's mkimage command, so passing the same load address and entry point and some extra parameters like this. You can do that in scripts if you want. Actually, to make a board support Falcon mode, you have to have a SPL start U-Boot function that's defined for that board. So that's usually implemented in board vendor board.c. And here's the most typical example. So if your board doesn't have it, this function, you won't have Falcon boot. So this typical example, if Falcon mode is enabled, we can check for the presence of a particular character on the serial port. We can also check the environment if that's supported in the SPL. Load the value of the boot OS environment variable and check whether it's yes or no. If it is, then you boot the OS effectively, otherwise you'll return 0. Return 0 means don't start U-Boot, so load the OS directly. In case you don't have enough space to fit the support for the environment in the SPL, you can make the SPL start U-Boot function simpler and just test for the presence of a character on the serial line. Or even if reading characters from the serial line doesn't work, you can just have the function return 0, which will cause the SPL to directly load a Linux. Actually, you may also need extra defines to be set, but you will find which ones are missing at compile time as seen in the next slides. A frequent question is how to fall back to U-Boot. So if that's supported by your board, you can hit the specified key on the serial console, and when you're back in U-Boot, you can disable the boot OS environment variable. That's it. Otherwise, you can try to cause the OS loading to fail by erasing the kernel binary and storage, and if needed, the SPL export output as well. And if this still doesn't work, recompile and update the SPL without Falcon Mode support. That will cause U-Boot to be loaded. And or temporarily modify the SPL start U-Boot function to always return 1. This way don't lose your configuration. So the first case we are going to study is booting from raw MMC. So here's a proposed storage layout. So at offset 0 of the raw MMC, you have the must boot record, of course, containing the partitions. You have the SPL RX at offset 128K. 256K you have the U-Boot image, and then the U image at the 2 megabyte offset, and then we have the start of the first FAT partition that's at 16 megabytes. Actually, we need here in our case a FAT partition to store the boot.bin SPL file. SAME5D3 6 actually doesn't support an SPL file on raw MMC, unlike on IMXX, so you really need a FAT partition here to boot from MMC, even raw MMC. Yeah, so here the default partitions on your SD card may not work, so you have to create them in a way that they are far away from the start, far away enough from the start to have enough space for the U-Boot and U-image. Actually, here it's advisable to start the partition offsets from a multiple of what is called the segment size that you can find on the preferred erase size attribute under sysbus MMC devices. Otherwise, every time you modify the files in the first partition, you may actually end up erasing the blocks or overwriting the blocks that are before, and that's bad for performance and reliability. So to begin with, here's the configuration for this mode raw MMC. So that's the U-Boot configuration. I started from the MMC dev config. So here are the settings like enable Falcon Mode, maximum SPL size, and a few other settings such as enabling SPL export, specifying where U-Boot is stored. That's a configuration parameter. And then in the .h file for my board, I have the location of the RX file, the offset actually, the size of it, the kernel image offset as well, and the location in RAM where to store the RX temporarily. So here are the steps to write to raw storage. So on your GNU Linux host, you'll use the dd command to write U-Boot at the right offset. Here we propose to use the same block size as the sector size to get the same offsets as in the table that we proposed before. You'll also write U-image with dd. As a reminder, here the SPL is copied to a boot.bin file in a FAT partition. That's separate. On your U-Boot target now, right after SPL export, you first will select the default MMC device for MMC write by using MMC list and then MMC dev number, so 0 in our case. You check the size of the RX by printing the FTD RX length variable. Devise this size by the sector size 512, convert it to hexadecimal, round it up of course, and use the value to save the RX to raw MMC with the MMC write command, passing the FTD RX address, the target offset in terms of number of sectors, and the size in terms of number of sectors. So be careful here. MMC write really takes a number of sectors as the last argument. If, as I did, you pass a number of bytes, you'll erase your FAT partition, so that's a disaster. Don't forget that. So here are the results on raw MMC. So in the reference test, we are loading ZImage and DTB using fat load and a 0 boot delay, as shown here. That's not completely fair because we still have the little file system overhead, but that's the standard and easiest way on MMC. We could also have loaded images from raw MMC, but that's very inconvenient. So let's compare to the reality here, and the best result we get to boot until this message is shown on the console is 3.45 seconds. With the Falcon Boot test, the best result is 3 to 19. So here we only save 261 milliseconds. That's a bit disappointing. So I actually added the instrumentation to the SPL to allow me to understand why the gain is disappointing. Actually, the time to load the kernel from U-Boot, so the full U-Boot from FAT, was 530 milliseconds, and I measured the time to load the kernel from SPL and on raw MMC, and it was more than 1 second. By adding instrumentation, I could know how much time it took. So here, obviously, the MMC driver in the SPL has poor performance. Is that because of a lack of DMA? I tried to enable DMA in the config options, but that didn't help. Note that we had much better results on different hardware, such as saving 1.2 seconds on IMX6 on a recent project, and 478 milliseconds on the BeagleBone Black. So that depends on the hardware. There's just an issue here that's probably worth addressing. Now the next case is to implement Falcon Mode from raw NAND. So I'm proposing this layout here. Actually, only the SPL offset is hard-coded. It must be at the start of raw NAND. All the other offsets can be configured differently. The only constraint is that offsets must be a multiple of the erase block size, which is 128 kilobytes here. So you see the offsets either in the U-Boot configuration. So we started from the NAND flash.config configuration, or in the board.h file that's here. So now the results on raw NAND. So for the reference test, I also used the 0 boot delay and the exact Z-image and DTB size at load time, not a pessimistic one. The best results is 4.32 seconds. With the Falcon Boost test, the best result, I guess, is 3.76 seconds. So here it's nice because we saved 552 milliseconds, which is a worthy achievement. So after seeing those examples, when it's your turn to implement Falcon Mode support on your board, I believe it's useful to actually read the code in common SPL, SPL-MMC, SPL-NAND.c, in the U-Boot source code, also other code in common SPL, to understand how U-Boot implements Falcon Mode, what is loaded first, etc., and how you fall back to U-Boot. So that's helpful. If booting doesn't work, and it won't at the first tries, I guess, the easiest way is to add puts lines to trace strategic functions and check return values, like when you load some objects, see if the right size, etc. You'll get the messages in the serial console, and that's really easy to implement. Now time to wrap up and look back at issues and lessons learned. So here in this particular case, we had an SPL storage driver performance that's worth investigating and limited the gains that we had on our platform. There's also the features that are limited by space. So what can be done with Falcon booting is limited not by the U-Boot features, but by how much code you can fit in the limited SRAM size. So that's why here I couldn't show Falcon booting from a FAT partition, because adding support for that file system and for disk partitions into the SPL didn't fit into the maximum possible size on the platform we chose for the demo. Another potential issue is U-Boot initializations. So in addition to the FDT fixups, without which the Linux kernel may not boot, the Linux kernel may also rely on some initializations coming from U-Boot. So before such dependencies can be removed by updating kernel drivers, you may need to hard code such initializations performed by U-Boot into the SPL, provided you have enough space. Another issue is the limited automation that we found in real-life projects. So while the UImage file can be automatically updated in the storage image, when you make any change to the kernel command line or the device tree, you must go through the SPL export command on the board to make the update. You can't really automate the FDT fixups that are done by U-Boot in your own scripts. They are not trivial to reproduce, so you need U-Boot to run those, and it makes it difficult to prepare production images without a manual step in U-Boot. Another issue is no decompression, so U-Boot doesn't seem to currently at least support decompression in the SPL. So if your architecture doesn't support kernel self decompression and relies on the bootloader to do it, such as on ARM64 or RISC-V, Falcon Mode won't be available unless you don't compress your kernel. On a side note, I've also found that U-Boot's bootem command was noticeably slower than bootz, plus 170 milliseconds. Now further work on this topic. The first thing is to work on improving the raw MMC read performance in U-Boot's SPL on microchip SAMe5. Something else I didn't try is what U-Boot calls the raw kernel images yet that are supported with config SPL raw image support. I assume this corresponds to the uncompressed image in Arch ARM boot image on ARM 32-bit. I didn't try fit image support in SPL yet. I will try it on an SoC with more space for the SPL, such as IMX. Now some further references in case you're interested in exploring this topic further and reproducing this. So first, there's the patch I sent to the U-Boot mailing list with my changes to support Falcon Mode on SAMe5D3 explained. There's also, if you're interested in boot time optimization, there's our Bootlin course on boot time optimization. And as usual with Bootlin training courses, all the materials are freely available on our website under a free documentation license. Of course, if you're interested in adding support for Falcon Mode on your board, we'll be delighted to help you too, of course. And with the general aspect of reducing boot time on your platforms. You can also have a look at U-Boot's doc readme.falcon file, which gives you an overview and the philosophy of the approach. And if you want to know more about how the ARM32 kernel starts, there's a nice blog post from Linux Valley as well. Hey, that's it. That's how you win the time war. Well, you may wonder about this red bird, this blue bird. Actually, if you attended this talk, I'm sure you're interested in time travel and probably in science fiction as well. So you may find out what book or novel I'm referring to here. So I'll leave that to you as a challenge. So I believe we have 7 minutes left in the talk. After the talk for questions, suggestions, and comments. So let's go ahead and chat. So thank you very much for your attention and enjoy the conference.